So now you've graphed all of these points. I just want to point out some features to us. The connection, we've hit actually two of our themes. So for instance, if you look at point A, which is on f of x, and the inverse of A, which is on the inverse function, what you'll notice, and I'm just going to use a highlighter, is that here's A, here's the inverse of A. They are a reflection about the identity line. If you don't believe me, just tilt your head 45 degrees angle, and if you reflect those 2 points, or if you reflect A, it goes into A inverse. If you reflect A inverse, it'll go back to A. Well, same with B. Same with C. D as well. So really, we've hit two themes. In inverse functions, the x's and the y's are switched. But also, when we have points, or more generally a graph, the inverse functions and or the function and its inverse will be the mirror image of each other. So building on that, we're just going to switch the x's and y's. Let's consider the following. Another way to think about an inverse function is that the independent x and the dependent y of f of x switch to become the dependent and independent of the inverse, respectively. The domain and range of f of x become the range and the domain of f inverse. Although this is complicated in words, really it's just a consequence of the x's and y's switching. The xy of f of x turn into the y and x on the inverse. They switch. Same with domain and range. However, we have to be careful about when we use the word inverse. I'm going to say all functions have an inverse, but not all functions have an inverse that is also a function. And an inverse that is also a function, we can call it a special name like inverse function. Not all functions have an inverse function. In order for f of x to have an inverse function, f of x must pass the horizontal line test. A function passes a horizontal line test is called one-to-one. A one-to-one function has each x value map into a unique y value. And each y value will map into a unique x. That is, for a given x, you only have one y value. That's a function. What makes it one-to-one is that now you only have one y, for a y value, there is only one x value that is possible. That's what makes it one-to-one. There's one x value for each y and one y value for each x. If we take a look at what I'm going to do next, I've just sketched this out. You may wish to stop the video, pause this out, and sketch this out. I'm just going to sketch f of x. Now I'm going to sketch f of x in, for those of you who have math professors or math teachers for parents, they're going to spot out an error here in notation. So here's f of x. F of x is just really a parabola. I've drawn my identity line. I'm not trying to make this too precise. I just want a quick sketch. What we see is if this graph would pass a vertical line test. So it is a function. But this graph fails a horizontal line test. That is, there's two y values there are two x values for a given y value. So that's not a one-to-one function, and therefore when we draw its inverse will not be an inverse function. So now I'm just going to draw the inverse function of this. And the inverse function of this, the inverse looks like this. So I'm just going to take this arm, and I'm going to reflect it. I'm going to take this arm, the left arm, the negative arm, I'm going to reflect it over here. What we can see is, if I call this an inverse function, well, it's an inverse, but it's not an inverse function. So since f of x was not one-to-one and didn't pass the horizontal line test, the inverse will not be a function. So I cannot use functional notation. I would maybe just want to call it an inverse relation right now. However, when this happens, sometimes we constrain the domain of a function. Allow me to draw g of x. Well, g of x is just a parabola. And I've drawn my identity line, y is equal to x. These two intersect at point 1, 1. What you'll notice is that my new function, g of x, actually passes the horizontal line test. That is, there's this one-to-one option. For every x value, there's only one y. And for every y value, there's only one x. It's really important. I'm going to graph the inverse, and what we see now is that we can say that we have an inverse function. Now, here's a good time to start saying, well, if g of x is x squared, that is, you're just squaring your input, well, what is the inverse or the undoing of squaring your input? I hear you. Some of you guys are yelling at home. Yes, it's the square root of x. So the inverse, by the way, this is what a square root function looks like. This is what a quadratic looks like. That makes a lot of sense. In algebra, if I square 3, what is the inverse of squaring it? Well, it's square rooting. So squaring and square rooting are inverse operations, and we can say, well, these two are inverse functions of each other.